chapter, we will introduce the solutions to partial differential equation. So in these brief sections, notice I gave you a lot of material, but actually they're very short sections. Uh, we will solve like really basic elementary partial differential equations and initial value problems involving partial differential equations. Well, first of all, let's define what a partial differential equation is. That is an equation involving derivatives of functions with two or more variables. That's why this requires some partial derivatives. Okay, well, as a first example, we're given some function typically for PDEs, that's short for partial differential equations. We use the dependent variable u, and the independent variables typically are x, y, z. Sometimes we include t, depending on the situation that is getting modeled. And well, for this introductory example, they're asking us to verify that the given function here is a solution to this partial differential equation here. Okay, so what do we do? Well, in this case, we're given the function, we need to take the necessary partial derivatives, the derivative of u with respect to x and the derivative of u with respect to y. So here we go. So the partial of u with respect to x, that equals the derivative. Okay, this is going to go to zero. There's no x's at all. Here, the derivative of the exponential is itself the exponential times by chain rule the derivative of the exponent with respect x, that is multiplied by -1. But I'm just going to go and write that negative sign in the front. So that is our partial with respect x. Okay. Number two, the partial of u with respect to y. That'll be, okay, what is that? Negative. Okay. Wait, no, not negative. That is, yeah, negative 2e to the negative y. And then the derivative of this with respect y, well, that's itself plus space 3e to the negative x minus 2y. But well, by chain rule, just multiply this by -2, which I'm going to do with the 3 to make it a -6. All right. How about that? I mean, just a basic chain rule here. Now that we have the derivatives, let's just substitute everything into the PDE, okay? That is, substitute the derivative with respect to x, that is -3, e to the negative x minus 2y, all right? Minus the given function u. I'm going to put brackets or parentheses, doesn't matter. The given function, which is u, 2e to the negative y plus 3e to the negative x minus 2y. All right? And then let that be equal to the partial derivative of u with y this time, which is what we just found before. That is -2 e to the negative y minus 6 e to the negative x minus 2y. All right? Okay, now let's check both sides of the equation. That is, okay, combining like terms, I'm going to go with, okay, -3e to the negative x minus 2y. Combine it with this another -3, that is -6e to the negative x minus 2y. And then minus 2e to the negative y. Well, isn't that a solution to the PDE? That's because both sides of the equation agree when checking and substituting everything. All right. So yes, it is a solution. Now the question here is, how do we solve that equation? Well, in the second section, in the next section, we're going to use a special case of separation of variables for partial differential equations, which is, well, you'll see. In the meantime, well, guys, it turns out that many methods that we learn to solve ordinary differential equations can also be used to solve some partial differential equations. You know, like the usual separation of variables, or even some of the elementary higher order partial differential equations that may resemble some of the ODEs. We can use those methods, but actually, In this, well, no, never mind, never mind. Okay, let's just get to solve some PDEs here. Okay, guys, when you're given, uh, okay, when you're given a PDE like this, the partial of u with respect t equals to 0. Well, I mean, you're looking for a function whose partial derivative with respect to t equals to 0. That's just a number, right? That's just a constant. But the thing here, it's never clear whether this u is a function, how many variables. Could be a function of x, y, could be a function of x and t, could be a function of y and t, could be a function of x, y, z, and t, could be a function of many variables. So that's why, notice we have some extra information. In this case, the function we're looking for is a function of x and t. All right, it's a function that models a situation in space, in the one dimensional space, and in the time domain. All right, that's what's going on here. Okay, guys. All right, so let's separate the variables here. So I'm going to du times 0 dx. I mean not x, dt. And then we'll simply integrate both sides. The integral of u equals to u. The integral of 0, okay, let's call it a 0t. I know the integral of 0 is 0, but there's some process I'd like to show you here. So plus some constant of integration, right? You guys agree with like a calc 1 integral essentially. Okay. But in this case, now that we are done with the solution to the PDE, now let's call this our u. Instead, u of x t, and 0 times t, that's simply 0. All right? So that's actually some c, okay? But that c instead is a function of the variable we didn't integrate with respect to. Notice we integrated with respect time, with respect t. So the constant will be really a function of the space domain, which in this case is some function of x. All right? Now, take the derivative of some function that contains all x's with respect time. Isn't that going to be 0? Because there's no t's at all. So that actually checks the solution. All right, so letter B. The partial of u with respect x equals to 9x squared y plus 3t cubed y squared. Well, in this case, what do we have? The function is modeling a situation in the two-dimensional domain x, y, and time as well. All right. Now, in this case, I'm going to do the usual separation of variables. Partial of u with respect, well, not with respect, that's just the differential. That's 9 x squared y plus 3t cubed y squared dx. Okay, so let's integrate. Let's integrate both sides. So the integral and the derivative symbol cancel out. That's equal to u. Okay, have a look at the first term. 9x squared y. We're integrating this with respect x. So the y is just a multiple constant, and then the integral of 9x squared is, what is that? 9x cubed over 3, which reduces to, well, let me do 9x cubed over 3 times y plus, okay, careful here, because this term right here, 3t cubed y squared, that's just a function of y and t, all right? So in this case, that's just a constant with respect x. So this simply will be 3t cubed xy squared plus some constant, okay? But this constant right here will be, okay, this constant c will be a function of the two variables that remain constant, isn't it? Since we integrated with respect x, this constant is a function of y and t, all right? Now, with the proper notation, let's just write our result as a function u of x, y, t equals to, reduce 9 over 3, that's 3x cubed y plus 3t cubed xy squared plus some function f of y and t. Or if you want to keep the letter c, that's fine. It doesn't matter. I mean, it's as long as it really represents that it's a constant, all right? That doesn't matter, all right? Okay. Hmm. So that's as far as first order PDEs. Okay, let's have a look at the next one. Now we have a second order PDE. And guys, some of the more advanced second order PDEs require deeper tools, deeper understanding in Fourier analysis and many other techniques that we're not going to do. But in this case, since this is a simple, relatively simpler type of equation, well, this is doable. So they're asking us for the function whose second partial derivative equals to e to the 3t sine 4x, where in this case, the function is it's modeling some situation in the one-dimensional domain, the space rather, and time. All right. So okay, now how do we manage the notation here? Now check this out. So do you guys agree that the second partial derivative can be written as the partial derivative with respect t of something that was already differentiated with respect t, right? So that is the derivative of the already derivative, right? This is called three, different ways to denote partials. Okay, so let it equal to e to the 3t sine 4x. Okay, I'm doing this so I can separate the variables, multiply both sides by dt. So that's going to be d, well, partial of the partial of u with respect t equals to e to the 3t sine 4x dt. So we can integrate both sides. The integral cancels the differential, leaving us with du or partial of u with respect t. And now let's integrate e to the 3t sine 4x, but in this case, with respect t. See the differential with the partial symbol? So sine 4x is a constant. All you need to do is integrate e to the 3t, that is 1/3 e to the 3t sine 4x. However, be careful. Call this plus some c1, okay? C1. However, and what am I doing the C1? Because we're going to integrate a second time, and that's going to spawn a second constant of integration. Now, we need to be very specific about this constant of integration. Since we integrated with respect t, this constant is a function of the other variable that was held constant. All right, that is x. So here we go. Let's perform the second integration. So partial u equals to 1/3 e to the 3t sine 4x plus c1 of x dt. And then just integrate both sides. Integrate. So the integral cancels the derivative. That's going to leave us with u equals to, well, again, all we need to is integrate we integrate the exponential. The integral of e to the 3t is another 1/3 e to the 3t times the 1/3, that equals 1/9 e to the 3t. Same sign for x. However, be careful because this constant, it's still a constant with respect t. So the integral of a constant is the constant times the variable, which I'm going to write like, okay, let me call it c1 of x t plus c2 of x. That's the second constant of integration because we're integrating twice. All right, well, I guess we're done with the solution. So all we need is just use the proper notation because u is a function in the one-dimensional space and time, that is 1/9 e to the 3t sine of 4x. Okay, let me make some space right here. And however you want to express these guys, I mean, this c1 xt c2 of x, you could leave it like this, or if you prefer, maybe call this uh, f of x times t plus g of x. It doesn't matter. It doesn't matter. Okay. All right, guys. Well, let's have a look at another example. Letter D. So the second partial of the function u first with respect y and then with respect x. Be careful with the notation. From Calc 3, the way we read these partial derivative symbols, whenever we have the Jacobian notation, this is the order of the differentiation from right to left, as opposed to when you have the derivative with respect y and then with respect x, you go in this direction when you use the subscript diversion otherwise. And if you're wondering why do we read it the other way around when we have the Jacobian notation symbol, that's because, okay, in a similar way that we did with the previous example, letter C, uh, this is the derivative with respect x of something we already differentiated with respect y. Now, how do we go here? We go from the inside out, don't we? So that's why we differentiate with y with respect y first and then with respect x. So that's why we go from right to left. All right. Well, so this is equal to e to the 4x over y. Okay. And in this case, well, the function we're looking for is a function of x and y. All right. It doesn't involve t this time like the other examples. I mean, doesn't matter. It could be anything, you know? Okay, so separate the variables. So the differential of partial u with respect y equals to e to the 4x y dx. I mean, if you want to switch to ordinary d's, that's fine. But this, since technically we're solving what's it called, a PDE, well, it's better to use the PDE symbol. Okay, so integrate both sides. Okay, cancel the integral with the partial derivative symbol. Du partial u with respect to y equals to, actually, let me not make it look like a 2. This is a partial derivative symbol, also almost looks like a 2. Here we go. Okay, so the integral of e to the 4x with respect x, that's 1/4 e to the 4x over y. Okay, so what do I do here? Actually, you know what? I'm going to go like this instead. 1/4 e to the 4x times 1 over y. It would be easier to when we do the second integration. So I'm going to multiply both sides by dy, so that is du equals to 1 over 4 e to the 4x, 1 over y. So integrate, integral cancels the partial derivative symbol, so u equals to, okay, 1/4 e to the 4x is a constant this time with respect y, so that's simply 1/4 e to the 4x. And what's the integral of 1 over y with respect y? ln, right? Huh? However, looks like I missed something, isn't it? What did I miss? I missed the constant of integration plus some c of x in this case, isn't it? Some c of x. All right. So, what is this? Plus c of x, isn't it? Then dx. So that's the integral. Okay. So yes, wait. No, that's with respect to y, right? With respect to y. All right. Okay, so that's some function c of x as an arbitrary constant. Okay, uh, plus c of x times y. But because of the second integration, we need another. Okay, this is c1. This. Oh well, actually, we don't need any. Um, okay. All right, well, let me go back right here. This is supposed to be a function of y because we integrated with respect x. So that's a function of y. It's a function of y. All right. And then that's a function of x. In this case, notice I didn't use the subscript c1 and c2. That's because these are functions of different variables. Okay, that's why. Otherwise, if both constants were functions of the same variable, like the previous example, we would have had to use a c1 and a c2, which later becomes some f and g. All right. We're done with the solution u of x, y. That is 1/4 e to the 4x ln y plus, let me call this, how about y g of y plus f of x, okay? Plus some f of x, whatever they are. They're just constants of integration. But these constants now have variables. Yes. Oh, I mean, yeah, we could do the absolute value or maybe not. Yeah, I'm going to do it. You're right. Maybe I should. Right? Much better. Um, that you're right about it because technically by absorption, right? That's a good observation. U of x, y, because this is y, this is a function of y. But you know what? Hold on, never mind. Actually, I'm going to leave it like this because, okay, what if g of y is y squared? Well, that can be multiplied into y to the fourth power, right? But what if this g of y is arctangent of y? Mm, that factor of y should remain there, right? It doesn't really get absorbed into the argument of the arctangent function. So yeah, so I think I would leave it like this. And that's because it's going to depend on the conditions to find g of y and f of x, which is, no, it's not the next problem, but the following afterwards. Okay, guys, well, so that's how we solve a couple of really basic second order partial differential equation. All right, what about the next one? So the next one should look familiar at the form because what do we have? The second partial of u with respect x plus 8 times the first partial derivative with respect x plus 25u equals to 0. Does that remind you of the homogeneous second order or higher order ordinary differential equations? Well, in this case, resembles, this resembles u double prime plus 8u plus 25u equals to 0. So that's why we can solve this problem using the ordinary differential equations techniques. However, guys, if for whatever reason you end up having one of these partial derivatives, okay, like in this case, the second partial with respect x, okay? However, if this derivative term were with respect y or with respect t, we can't solve this problem any longer with this method because those are partials with respect different variables. So that's actually a very advanced problem that's beyond the scope of our course. Okay, so what do we do to solve this problem? Remember, write the auxiliary equation m squared plus 8m plus 25 equals to 0. And well, are there factors of 25 that add up to 8? So just 1 and 25, that doesn't add up to 8. 5 times 5, that doesn't add up to 8 either. What do we do in this case? Quadratic formula. So m equals to -8 plus or minus the square root of 8 squared, x squared minus 4 times 1 times 25. Okay? So that is going to be 6, everything divided by 2 times 1. That is -8 plus or minus the square root. 64 minus 100. What is that? -36 over 2. Square root of -36. That's -8. What is that equal to? Plus or minus equals to 6i, right? This is one of the imaginary ones. Over 2, which reduces to -4 plus or minus 3i. All right. So what was the solution to this kind of equation? And notice in this case, this is, we're looking for a function of, well, I mean, for a function of x and y, and the variable that changed in this case, it's x. So we can simply go, okay, what was that? Remember the alpha? Remember the beta? So u equals e to the alpha x times c1 cosine beta x plus C2 sine beta x, okay? And just substitute what you know, all right? Which is u of, in this case, okay, u of xy, all right? U of xy, now I'm going to go to the final solution, e to the alpha, which is negative 4x. Okay, what are these C1 and C2? These are two functions of the other variable that actually remain constant when when we were solving the DE, isn't it? What was that variable that remained constant? So you can call this. I'm gonna call this one this time a C1 of y cosine 3x plus C2 of y sine 3x. I mean, ultimately, you can use whatever notation you want. Maybe, okay, maybe f of y for C1 and f and g of y for C2. All right. Those are two different concepts because second order. All right. All right, guys. Now, you might be wondering, how do we find this functions that are technically constants of integration? Well, that actually reminds us to solve an initial value problem. And well, let me give you an example on the next page. One example about it. Okay. So solve the initial value problem. Also, sometimes they call this boundary value problem, depending on the situation, depending on the idea, but let's call it an initial value problem. Okay, so so they're asking us to solve this second order partial differential equation by basic integration. All right, by I mean, it resembles a lot a separation of variables from the beginning of the semester. However, we will soon discuss a separation of variables that has not much to do with the separation of variables you already know. Okay, so now they're giving us two conditions. So once we solve the differential equation, use u of 0 y equals to e to the y, and the partial of u with respect x evaluated at 0 comma y equals to arctangent of 0, which is like, what hell does that mean? Okay, remember those problems, y double prime plus 5, y equals 0 with y of 0 equals to 5, and y of 0, or y prime equals to, say, 3. So those are the initial conditions that you would use to obtain the constant C1 and C2, right? Well, in this case, because these constants are no longer just numbers, just constant, those constants are functions of potentially multiple variables, guys. I mean, doesn't it's not, I mean, it could be like that, all right? So how do we go about this? Well, first of all, solve the PDE. Okay, solve the PDE. Partial with respect x. Change the notation first. Equals 4xy. I'm going to separate, I'm going to multiply by a dx. So that's the differential, the partial differential of the derivative of u with respect x equals to 4xy dx. All right. So that means integrate both sides with respect. Well, integrate right here, cancel the integral symbol with the partial derivative symbol, and integrate with respect x. So that'll be partial u with respect x equal to uh, the integral of 4xy with respect x. That's actually 2x squared y plus some, let me call this, actually, you know what, guys? I'm going to go straight to some function f of y, okay? Because we actually have some conditions already, okay? So what does that mean? Now let me separate the variables again. Let me solve for du equals to 2x squared y plus f of y, but now this time the x. Integrate both sides. All right, integrate both sides. The integral and the differential symbol cancel out, and that gives us already the function u, which is a function of x and y, by the way. Well, it didn't say in the original problem. However, given the conditions, I think by alphabetic order, this is some x and this is some y. There is no other variable involved, so I think it's easily figured that it's just a function of x and y in this case. Okay, so the integral of 2x squared with respect x. So isn't that what's it called? Uh 2x cubed over 3 y plus f of y times x plus some other constant that I'm gonna call, how about g of y, right? Another g of y, another function of y. And guys, this is our general solution, right? This is just our general solution. Actually, all problems we solved before were general solutions to the problem. We didn't find those constants. We will in this exercise right here. All right. So how do we okay? How do we apply the given conditions to find f of y and g of y? Well, in just the same way you evaluated the solution at 0 and you set it equal to 5 to find one of the constant, and then the derivative at 0 set it equal to 3. Well, what are we going to do? We're going to evaluate at 0y and set it equal to e to the y. How are we going to do this? Okay, check this out. So this is new for you guys. It's essentially the same process we did before, but this might be new due to the number of variables we're handling this time. But essentially works the same way. Okay, so I'm gonna go and evaluate u of 0 y. Okay, so from the general solution, I'm going to replace every instance of x with a 0, and we're going to leave the y variable untouched. All right, that is 2/3 times 0 cubed y plus f of y times x, actually times 0. Let me do dot 0 plus some g of y, whatever that is. Okay, because of those multiplications by zeros, the first two terms actually go to 0, isn't it? Goes to 0, goes to 0. Okay, so but what's u of 0y, guys? From the conditions, that equals e to the y, isn't it? Okay, so that is e to the y, and that is equal to g of y. So that is the constant of integration g, which in this case is not just a constant, not just a number. It's actually a function of y, which is a function of the other variable that remain intact when integrating the PD. Now, we need to evaluate u with respect x of x, y. Actually, we have it already, don't we? It's this. Or take the derivative of the solution with respect x. So that'll be 2x squared y plus f of y plus f of y. All right. Well, so let's substitute the conditioned u sub x of 0 y. What does that mean? To the partial derivative of the general solution, which is what we had over there, which is what we got over there, change every instance of x with a 0, that is 2 times 0 squared y, and every y remains intact. Now, what is u sub x of 0 y? Isn't that equal to the arctan function here? So that is arctan y, and actually this goes to 0, and that is equal to f of y. Okay, all right, guys. Now we're ready to write the particular solution because arctan y is our f of y, which is going to go here, and g of y equals e to the y So just back substitute two, and that's it. All right, that's it. So u of xy equals to 2/3 x cubed y plus, I'm going to write the x in the front of arctan, plus g of y, which is e to the y. And that is our final answer. This is actually our particular solution. And you can verify the equation. Take the derivative of that function with respect x twice. That should give you the original equation here. All right. Okay. Looks like that's the end of the section, isn't it?